Okay, thank you, RDIA, for the invitation and for giving me this opportunity to share with you some of our work in the area of space. So probably you all are familiar with the space race, even the deep space race. In another context, the deep sea race. What you are probably less familiar with is a near space race that is going in the background. I will define that as we progress in this talk. So I am by training, sorry, I'm having, it's not working. Yeah, oh, okay, yes, okay. So I am by training a wireless telecom engineer. So the motivation is a more of a connectivity and telecommunication motivation. But obviously, as you will see, what I'm talking about is beyond connectivity and beyond telecommunication. So as you know, we are at a time where 6G is at the last stage of being designed. Actually, next month, in March, in Korea, 6G vision will be finalized, and we all know what 6G will be about. And in big part, or at least one important aspect of 6G in comparison with 5G, is that 6G is going to do hopefully much better in addressing the connectivity divide that the previous generation of wireless communication system suffered from. As you know, now we live in a world where still we have about 1/3 of world population that are unconnected or underconnected. We are talking about nearly 3 billion people for multiple reasons that are beyond the scope of this discussion today. But 6G is trying to make sure that we connect more of these unconnected. And when we talk about that, obviously we are talking about people in rural areas, developing countries, but actually we are talking about many other aspects. We have heard this morning a lot of interesting talks about cognitive cities. We want to talk about in a more general framework about cognitive villages, cognitive hamlets, cognitive rural area, and more generally cognitive environment and cognitive or smart living. And again, as mentioned this morning, when you want a cognitive environment beyond data and AI, you need an infrastructure, and telecommunication connectivity is at the core of creating an infrastructure that enable intelligence, enable these cognitive environments. When you connect the unconnected, indirectly you are solving multiple other problems. Let me give you some examples. Those of us who live in a very well-connected environment, we tend to forget that this connectivity can be lost overnight because of a natural disaster, an earthquake or volcano that can destroy the ground infrastructure. So you will need to bring connectivity, as you will see, from the sky or from the space. When we talk about smart farming, we are often talking about unconnected environment that are not covered by cellular type of connectivity. And again, connectivity from the sky can be very helpful. Special events. What do I mean by that? We mean that this tendency to densify the network, this is well known in telecom engineering. If you have more density population, you put more base station. At some point, this is not sustainable anymore. What is the point of putting base station everywhere in an environment where basically traffic is very dynamic? Isn't it better to kind of put your ground infrastructure for mean type of traffic or average type of traffic and support extra needs, special events, like for instance, like a concert or a final of a match, a football match, by bringing some connectivity from the sky on demand. That connectivity can be brought or taken somewhere else at the end of that event. So these are many examples of scenarios where basically we need to connect the unconnected in different kind of context. So now, one of the main challenges when we try to connect the unconnected is summarized in this very simple block diagram, where it shows the quality of experience as function of the cost per user. In particular here, we are focusing on remote low population density area. We all know that optical fiber cables are the main engine behind internet revolution in dense urban environment. But it doesn't make much business sense to dig and lie basically 100, if not thousands of kilometers of fiber to reach these remote zones or zones that typically are sparsely populated and often low income. Satellite, in their early generation, have been designed mostly for broadcasting, one-way broadcasting, like TV broadcasting. They are still quite expensive for two-way internet connectivity. So the kind of holy grail that we are trying to solve in terms of global connectivity is how can we achieve a good quality of experience at a low cost, even for these low population density areas. Now, and with that, what you need to do, you need to bring connectivity from a high altitude to gain in coverage. So obviously you can start building towers. At some point you cannot build Eiffel Tower everywhere. So you need to go to the space or to the sky. So what most of you probably are familiar with is a well-known now space race with Starlink, OneWeb, Kuiper, which is the Amazon version of Starlink, and it's coming online sometime in 2025, at least according to their kind of announcements. The Canadian Lightspeed Constellation, the Chinese G60 or GW. There are plenty of basically satellite constellations that are being launched and that will constitute this umbrella that will bring connectivity. And that's what's well known. What is less known is the near space, where basically this connectivity that we are all after can be brought from platforms that are active at 20 kilometer altitude. For calibration purpose, the airplane that we use to fly around are flying at altitude of roughly 10 to 12 kilometers. These are platforms operating in the stratosphere, way above airplanes. They can come in different form, balloons, airships, or actually aircraft in the form of gliders or just standard aircraft. They are either solar powered, but people are looking, and that's where the race is going, how to create power in the stratosphere, for example, using hydrogen fuel cell. This is an active research field, and actually not only research, but I would say industrial development field, where multiple companies and big players are trying to build this infrastructure. So why I'm talking about infrastructure? Because I would like to highlight, although I am a telecom engineer, that we are talking here about an infrastructure project in the stratosphere where applications are beyond telecommunication. Telecommunication is one popular, basically, of course, application. For instance, here in this infographics, what we are showing an area that is subject to a disaster, like a flood. Some people have been moved to this refugee camp, so you can connect them with these green beams. You can also use another HAPS. So HAPS stand for High Altitude Platform Station. Sometimes it's also known as High Altitude Pseudosatellite. They are, again, the stratosphere. They are not on orbit. They are still within air or sky. They are not in the space, so they are not on an orbit. So you can have multiple of these HAPS. Each one of them can have tens, if not hundreds of kilometers of coverage. So you can use them for IoT applications. But again, re-emphasizing the fact that we are talking about an infrastructure in the near space. You can put a camera attached to this HAPS for border control. You can attach a LiDAR for environment monitoring. You can have a radar for disaster impact. At the end of the day, a HAPS has a payload. This payload will have a certain swap parameter, size, weight, and power, and will be kind of sent for not only a mission, multiple missions. Some of them are communication mission. Some of them are sensing mission. There are actually even some startup looking at power transfer missions. And we can talk about that if you're interested offline, how you can use HAPS for connectivity, for sensing, and for power transfer. So I can spend, like the full hour telling you why HAPS are interesting and why they do present a clear advantage. But I will give you two examples where really HAPS have an advantage and why their potential is great. Number one of the key features that everyone is after when we talk about satellite communication is direct-to-phone communication. When we talk about direct-to-phone, we are not talking about old Thuraya type of generation of satellite where you have direct-to-phone, but that's a special phone. when you read in the news about direct to phone is how can your 5G phone, the same phone that you're using for your Wi-Fi connection, your 5G, eventually 6G connection, can be automatically used without any change from your side to connect to a satellite. That's what we are calling direct to phone. As of now, Starlink actually is offering basically direct to phone, but it's just texting. They really recently announced voice. But what is the capacity? Can you really offer it at a big scale? Can we do broadband? That's a challenging proposition. Just because the best satellite from a budget link is at 100 kilometer cannot just offer the right SNR to basically close the link and offer the kind of data rate that you would like to have to be able to have a broadband communication. There are smart people looking at multiple options, such as beamforming for multiple satellites, or sending basically antenna that are folded and that unfold, and then basically create this football stadium antenna to be able to create the gain that you want to connect to a standard phone. But perhaps at 20 kilometer gives you a natural, basically, and much more friendly budget link to basically enable high capacity, high data rate transmission. That's example number one, or like an advantage number one. Advantage number two is a sustainability advantage or a sustainability argument. As you know, and I really mean it, we are talking about thousands of satellites, not tens, not hundreds, between the Kuipers, the OneWeb, the Starlink, the Ravane, and every day you learn about a new constellation. The question is, we are creating all the space debris, and there is a whole other economy that is building on how to collect all of these satellites that basically, once they are gone, they are lost pretty much. After 5 years, you have to replace them. At the end of the day, a HAPS is an aircraft or a balloon. It goes for a mission, it stays there for weeks, months, it comes back. It comes back, it can be maintained, it can be upgraded, eventually it can be retired. So that's another important argument that the HAPS industry can present, and that's why, again, the potential is there. Again, there are many other interesting advantages and also some disadvantages that we can talk about, or maybe challenges that the HAPS industry has to overcome to become a reality. But overall, I think it's an interesting proposition that we have to keep in mind. Now, just I want to highlight the fact that an experiment was done in the Red Sea Global, 4 hours north of our campus in KAUST, in collaboration with CST. Dr. Mohamed, who is the current head of RDA, was in CST, and he was the initiator of this experiment. We contribute from KAUST in terms of designing some of the experiments, and basically we wrote this paper demonstrating one of the first 5G connection from a phone to a HAPS in collaboration with Dutch Telecom and SPL, which is a British startup. And just one highlight of the experiments that were conducted. So you have a base station on the ground, another similar base station but attached to a HAPS, and you have the car moving away from these two base stations. The blue link is the link coming from the terrestrial base station. The magenta link is the link coming from the HAPS base station. As you see, as you move away, at some point, of course, the terrestrial link is going to die because you don't have the right line of sight and so on, whereas the HAPS links maintain a very good throughput. Actually, colleagues at that time in CST were able to connect from a boat, even from a helicopter, way far from a HAPS. So that's an illustration what HAPS can provide in terms of coverage compared to terrestrial base station. Now, in terms of research, I mean, I don't have the time to tell you about many of the research activities we are doing at KAUST. Professor Ahmed Tawil, myself, a few other colleagues worldwide are very active in the HAPS area. But one example here is a kind of a resource allocation problem, where we can use classical optimization, and of course now with AI, all the students want to use AI, so we did use AI to come up with good optimization ways. So here the paradigm we are trying to solve, we have a user, and the user has a choice to connect to the close by terrestrial base station or to the HAPS. How do you allocate users? How do you allocate power associated to that, and so on? Just to make a long story short, this is a deployment where we have a highly dense urban area, is some kind of suburban or village, and rural area in between. we are increasing the level of power. It's a downlink coming from the hubs from minus 40 dB watt to 30 dB watt. Basically, the Starlink, the pink here circles denote connectivity to terrestrial base station. So you see here, of course, in downtown, that's what we do, in village also. In some rural area close to base station, you are able to connect to this base station, but you have multiple unconnected users here. The blue rural users are unconnected because the level of power coming from the hubs is not enough. If you are able to generate more power, here from minus 4 dB watt to 10 dB watt, you are connecting all the rural users. But here, the beauty of the result is that if you go even further and give the hubs even more capabilities, then not only you connect all the unconnected, but you do offer better connectivity option for people in the cities, in the sense, better data rate. So this is in complete agreement, alignment with our vision for 6G, which is about connecting the unconnected and super connect the already connected people. So that's an illustration of what hubs can offer. So with that, I would like to conclude my talk and share with you our vision for the future for what we call a stratospheric cellular network, how we can take the cellular network we have on the ground and just copy it, but scale it at the scale of the stratosphere, where base station will be attached to hubs that will be interconnected with free space optics to create this huge network that can cover much larger area than cellular network covered today. With that, I would like to thank you, and these are some of the basically web page and LinkedIn page where we can follow our research, and I will be happy to take some question offline.